Greetings, trigonometry. Today we're going to be going over chapter 3.4, 3.5, and 3.6. We're going to start off with 3.4, the inverse trigonometric functions and right triangles. So these will be how we look at inverse trig functions as they pertain to right triangles. So here we've got the SOHCAHTOA, just like we always have. And we also will note that if we apply the inverse operator, we'll get this. So that the inverse sine acts on the opposite over the hypotenuse, the inverse cosine acts on the adjacent over the hypotenuse, and the inverse tangent acts on the opposite over the adjacent. Okay, and a little misspelling there, but that's all right. We know what it says. So we're going to just kick this off with one quick example. And this comes from problem 41 on page 200. And we have a 680-foot rope that anchors a hot air balloon. And we want to express the angle theta as a function of the height of the balloon. So let's go ahead and draw this guy out. We've got our hot air balloon right here. And it is some particular height. Right here, I mean it's free to, blow around in the wind, and so it's got a rope holding it down like so. And that rope is 680 feet. And then we've got our ground right here. And we note that it does form a triangle. And not just any triangle, but a right triangle. And so, again, we're trying to find theta as a function of height. All right. So first we set up our equation like we normally would. We've got theta here. We're looking at the adjacent side, so that's going to be sine theta equals h divided by 680. And so theta equals the inverse sine of h over 680. And there we go. There's our answer right there. Not too tough. Let's go ahead and look at this on a graph. Okay, and here we have the function graphed out. Here is the equation we have set up. Note that I have put a restriction on here that the height must be positive. This is because it doesn't make much sense to have a negative height, does it? And if we did include that portion, we would simply have, this portion of the graph here, which of course would be garbage, as the hot air balloon is not going to pass through the ground. So we want to make sure we have that restriction in there so that we have a function that makes sense. All right, so the next part of the question was, what is the height at 500 feet? So for this, we just take our function and plug in 500. All right, well, Desmos doesn't like it if you use theta, so I went ahead and changed it to a t here and here. And so the answer to that question is about 8.26, and you can see it on the graph right here. 8, if I get it to stay. Well, it's going to be 8.8261 and some change after that. So let's go ahead and put that into our response here. 0.826 is the height of the balloon, or the angle of the balloon. and we note that that is just short of 1 radian. So if we were to look at it angle-wise, that'd be something that looked about, see, not quite, or definitely less than 60 degrees, so it would be somewhere at that angle right there would be our balloon. Alright, I want us to look a little bit more at that graph. You may have noticed that I have some other things listed over here. We're going to go ahead and zoom out. Alright, so here we've got the a graph is the height of the balloon as a function of the base, as we have right here. This goes back to that, basically this is the Pythagorean identity. So for any, and what we mean by base is how far to the left or to the right the balloon is from the point that it's tethered down. And as you can see, that this guy right here, this will give us an actual XY position of the balloon. And you'll notice that it follows the path that we have set up for this graph right here. So hopefully this gives you kind of an idea. You can kind of what's going on. You can imagine this line right here as the rope holding on the balloon. This is the location of the balloon. And of course this is the height. And then this would be how far you are from the tethering of the balloon. So there we go. Nice little demonstration there. So we now move on to the law of sines and law of cosines as outlined in chapter 3.5 and 3.6. A little bit of jumping around this next part between those two sections, so I just have them both listed right here. So we're going to be looking at triangles that look like this guy right here now. Note there is no right angles. This is what we call an oblique triangle. And an oblique triangle has no right angles. No right angles. Though we can still use trigonometric ratios to figure out what the sides are. And so we typically have them set up like this. We'll call this angle alpha, and that would be side A. We would call this angle beta, and this would be side B. And then we'd call this side, or this angle gamma, and this would be side C. And so you can, if you put the side A in a different spot, that's fine. What you kind of want to make sure is that alpha and A are always opposite to each other, beta and B are opposite to each other, and C and gamma are opposite to each other. And this is just for convenience sake. When you're looking at it, you automatically know that gamma is going to be opposite to side C. Alright, so we've got 4 different cases that we are able to solve. The first one is ASA, which stands for angle, side, angle. Alright, and so in this case, you have a combination here. So we'll say we know this side. And let's say you'd know this angle here and this angle here. Alright, angle, side, angle. And we also refer to it as side, angle, angle, and that's just where you'd have one side followed by 2 angles. The next one is side, side, angle. There should be an S right there, so side, side, angle. And in this case, you have 2 sides, like so, and then you know one of the angles. It can be either this angle here, or it could be that angle there, whichever one it is, doesn't really matter. Okay, and then we have side, angle, side. So this one we've got 2 sides, like we did before. And we know the angle right there. All right, the next one is where we just know all three sides. And it looks like that right there. So again, the highlights simply mean the parts that we know. Okay. So we can solve the angle side angle and the side angle angle. Note that these are kind of both constitute the same case. We can also do side angle, right? So with the law of sines, we'll be able to knock out either of those two right there. Now, with something called the law of sines. Now, what is the law of sines? Law of sines is simply if you have sine of A and alpha, and you divide that by A, and that's going to be the same as sine of beta divided by B, which is the same as sine of gamma divided by C. I think the book doesn't use the Greek letters. If you're following along in the book, the way the book reads it as they've got a capital A to stand for the angle and a lower a to stand for the side. This is pretty common to see, so this is what we're going to go with. But just know that the book has a slightly different nomenclature, but it doesn't change the meaning at all. All right, so let's take a look at this guy. We're going to call this alpha, which makes this side A. We're going to call this beta, which makes this side B. And we're going to call this gamma, which makes this side C. All right, so to prove this identity, we're going to go ahead and use the area of a triangle equation. But we're going to do a couple different expressions for it. So, right, this would be the height, which again is going to equal B sine gamma, right, area of a triangle, 1/2 base times height. So it's simply 1/2 AB sine gamma. And note that the letters A and B, it's always the ones that are both adjacent to the angle we're looking at, just kind of the way it goes. So keeping that in mind, we're going to do the same thing for each angle. So we have 1/2. So H in this case equals A sine beta. Which gives us 1/2 AC sine beta. And kind of using that same pattern we were looking at before, we'll just go ahead and jump to the last expression, which is 1/2 BC sine alpha, right? Looking at these two guys there. All right, and so from here we simply simplify. We note that there's a 1/2 in every expression, so we can get rid of that. And then we're going to divide everything by ABC. So the first guy becomes sine gamma divided by C, since that's the only thing that's left. This second expression here becomes sine beta divided by b. And this last expression, we're going to divide by ABC. The b and c both cancel, and all we're left with is the a. And so that becomes sine alpha divided by a. And there's our proof. Okay, so let's go ahead and use this now. We're going to use this to find the missing sides of this particular angle, side, angle, triangle. So again, we want to know what this side is. We'll call this side A, and we'll call this side B. So using the law of sines, we use what we know. We should probably figure out what this angle here is going to be, because that will be our term that we do now. And again, this is just 180 degrees minus 75 degrees minus 60 degrees, which means that missing angle is 45 degrees. Okay? So now we go ahead and use our equation. Sine of 45 is the same over 340, right? We're just relating opposite angle to opposite sides, which equals this guy now. Sine of 75 degrees divided by our unknown side b. And then we look at this next one. Sine of 60 degrees divided by our unknown side a. Alright, so keep in mind this represents two different equations. This guy equals this guy, and this guy also equals this guy. And so we'll solve them independently of each other. When we do, we find that b equals sine of 75 degrees divided by sine of 45 degrees multiplied by 340. And then we find that a equals sine of 60 degrees divided by sine of 45 degrees multiplied by 340. Note that this amount and this amount are the same. Only difference is this guy and this guy. Okay, so when we run the calculations for both of these, we are going to get, gives us 464 and 416. Alright, let's go to our next example. We've got to find the missing sides of the side angle triangle. Alright, so again we're going to use the law of sines. So here we've got 20 degrees, so we'll call this over here side A, and we're going to call this side B. So first let's go ahead and work with the low-hanging fruit, so to speak. Let's go ahead and find that angle. So again we have 180 minus 25 minus 20, and these are all in terms of degrees. Then it's 135 degrees. Let's go ahead and write that down there. And then we set up our law of sines. All right, we have that guy there, and so we have sine of 135 divided by b equals we have that one there. Of course, we're not including there we go. And so that way, this one we've got sine of 20 degrees over class we're at the 25 degree guy, and we are including this guy here. And so that will be sine of 25 degrees divided by 80.4. Alright, good. So we've got ourselves one that is completely known. That will be a constant figure. Sine of 25 degrees divided by 80.4 is a constant number. And so let's go ahead and solve for both a and b using this relation. And so here we've got a equals sine of 20 degrees divided by sine of 25 degrees multiplied by 80.4. And then we have b equals sine of 135 degrees divided by sine of 25 degrees multiplied by 80.4. So again, note that we have our constant term right there. Okay, so now we need to go ahead and calculate through these guys. And the first one will be 65.1. And then the second one will be 134.5. Okay, and that's it. That is using the law of sines for using these two cases. Now we have two other cases to look at. We will be looking at these cases now, and for these we can use what's known as the law of cosines, because the law of sines will simply not be enough. And so for the law of cosines, this is how it goes. First off, let's go ahead and set up our triangle. This is side alpha, angle alpha with side A, and here we've got angle beta with side B, and here we've got angle gamma with side C on the opposite. And so the law of cosines goes as follows. We've got a squared plus, equals b squared plus c squared minus 2bc cosine alpha. Okay. So note that whatever angle you're looking at over here, the opposite side will be over here, and then the two other sides not associated with A will end up over here. Note that if alpha were a right angle, that is 90 degrees or pi over 2, then this breaks down into the Pythagorean theorem. All right, and so we have one for each angle, of course. B squared equals a squared plus c squared minus 2ac, and this would be cosine beta. Again, opposite side of the angle right there. Alright, and then finally we've got c squared equals a squared plus b squared minus 2ab times the cosine of beta. Alright, and there we are. Those are the three variations of the law of cosines. Note they all have exactly the same form, so there's no need to memorize three separate equations. Let's get into where the law of cosines comes from. Okay, so to prove this guy, what we're going to do is we're going to drop a line straight down forms a 90-degree angle. And note that how this is going to break our side C into two different sides. It's going to be a C1 and then a C2. Like so. So now we need to establish a few relationships here. And don't forget we got a height right there. We're going to set, first off, we note that C equals C1 plus C2. And we have a relationship for C2. We're going to be trying to solve for this guy here, so we want to get our include the angle alpha in there. So C2 equals B sine alpha. Sorry, cosine alpha. B cosine alpha. All right, and then we want to get something established for C1, and for C1 it simply equals our big C minus C2, which is our C minus B cosine alpha. All right, relating the heights is what we're going to be doing here. So we're using the Pythagorean theorem, so h squared equals a squared minus c squared and then looking at this triangle as our basis, it also is going to be b squared minus C2 squared. Make sure you have C1 squared, C2 squared. Okay. So those are our two height. We have them related to each other. Now all we're going to be doing now is substituting values in. C1 we have given right here. And then C2, we have given right there. So let's go ahead and substitute these through. And so we have a squared minus, let's go ahead and expand this while we're at it, c squared minus 2bc times cosine alpha plus b squared cosine squared alpha. All right. And again, we expanded that term out, and we're going to do the same thing with the C2 that we have highlighted in green. And this equals b squared minus b squared cosine squared alpha. Alright, so notice that we've got, minus negative b squared cosine squared alpha on the left, and then minus b squared cosine squared alpha on the right. So those two are going to cancel each other out. And now we're going to rearrange the equation so that we've got only a on the left-hand side and everything else on the right. And when we do that, we get a squared equals b squared plus c squared minus, right, because we have minus makes us a plus, then we subtract it on over to here. So minus 2bc cosine alpha. Same as we have up here. And you can prove the other two by similar methods, but we'll just stop right there because that is enough for what we are attempting to do. So let's go ahead and use the law of cosines to solve a side angle side triangle, and we want to find the missing side and angle. Angles. So first off, let's go ahead and identify or label some of the angles. We're going to go ahead and call this side A, and we'll call this angle beta here, and we'll call this angle gamma. Okay, so those are the three things that we are trying to find. Let's figure out beta first. All right, so which means we'll be using this equation. And so we've got, b squared is equals. Okay. Now, in second, let's find a first. I think that'll be a better use of our time. So we've got, which means we're using the original form of the equation, but note that each three has the same form, so it's not too hard to switch back and forth. So we have a squared equals b squared plus c squared minus 2bc cosine alpha. Alright, so let's go ahead and plug in what we know. B, we know that's given right here. C, we know that's given right there. And then alpha, we also know, given right there. So you can see clearly everything we know. It's just a simple plug it into the formula and work it through. So let's go ahead and do that. This equals 10.5 squared plus 18.0 squared minus 2 times 10.5 times 18.0, and then we're taking the cosine of 46.5. When you plug this into your calculators, and I do expect you to be running the calculation with me, make sure your calculator is in degree mode for this to work. And when we run through this, we find that the answer is about 174. And we'll go ahead and include some of those decimals since we're going to need those for our next set of calculations. Alright, so there we go. We've got one of our answers right here. Right, we're looking for this one. We got it right there. Next, now that we have A, let's go ahead and find beta. And so for this one, we again will be using the law of cosines. Okay, let's go ahead and color code that one as well, I guess. We'll make this one nice purple. There we go. And so for beta, we use b squared equals a squared plus c squared minus 2ac times the cosine of beta. Alright, so let's go ahead and highlight what we know. We know A, of course, since we just found that. We know B. We know C. Okay, and that is everything. So all we got to do is solve for beta. we do this, we have that beta equals the inverse cosine of b squared minus a squared. Sorry, a squared plus c squared minus b squared, all divided by 2ac. Right, all we're doing is just rearranging this equation here, which is the inverse cosine of 13.2. Alright, I didn't realize I'd hit the pause button, so I don't know how far I went, but we went ahead and ran through the calculation here. We've got 35.3 was what we ended up being the angle for beta. And now we're going to use the fact that there's 180 degrees in a triangle to find the last angle gamma. You could use law of cosines again, but this definitely seems like the easier option. And when you do that, you'll find that gamma is going to be about 98.2 degrees. Kind of running out of color, so I'm just going to circle it like so. Okay, and there we are. That's that example using law of cosines. The next one, we're going to deal with the final case, the side-side-side triangle. All right, we'll call this angle alpha, making this side A. We'll call this angle gamma, making this side C. And then we'll call this angle beta, making this side B. Alright, so we're going to use the law of cosines. Let's go ahead and use it to find alpha first. So we have a squared equals b squared plus c squared minus 2bc times cosine alpha. Okay, and so color coding, A to A, B to B, and then we've got our C's right there. Alright, so note that all we have to do is solve for alpha, just like we did before. Alpha equals the inverse cosine of b squared plus c squared minus a squared, all divided by 2bc. Alright, so now we just plug in all of our values. So we have 8 squared plus 12 squared minus 5 squared, and that's all divided by 2 times 8 times 12. Okay? And then we run through that calculation, and you will end up with about 18 degrees. Again, make sure your calculator is in degree mode and not radian mode. Alright, so this is going to be pretty much the same setup for beta and gamma. So for beta, let's go ahead and just set it up. All cocked and ready to go. Inverse cosine of a squared plus c squared. Notice that these two sides are just the sides that are positive are not the side opposite, and the side opposite is being subtracted. And then the two adjacent sides right here. And there we go. Pretty straightforward. And we plug in everything. So that we got 5 squared plus 12 squared minus 8 squared, and then that's all divided by 2 times 5 and 12. Okay? Put this in the calculator. Again, make sure your calculator is in fact in degree mode, and you will end up with about 29 degrees. Okay, and now for the last one, set it up the same way. Gamma is the inverse. Well, actually, I guess we don't need to set it up this way, because we could just use the fact that there's 180 degrees in a triangle. So we've got the fact that gamma is going to be 180 degrees minus 18 degrees minus 29 degrees, and that will get us 133 degrees. Alright, and there we have it. We used law of cosines to find the angles in a side-side-side triangle. So now let's talk a little bit about one final case. This is the ambiguous case, the SSA or the ASS. It's called the ambiguous case because it's not, you don't necessarily have a direct answer to the question or to what a proper triangle might be. So I've drawn out, what we have here. We've got, again, side, and then we have sorry, we don't have this side. We've got this side, and we've got this side, and then we've got that angle right there is what's known. That's going to kind of be the case for each of these. Let's look at the first one. So what we notice immediately, if we're given just any kind of random angle side, it could be too short, right? There's no way to make this work, because this leg that you see right here, this leg that you see right in here is locked into place by this angle. And so there's no way to bring this leg down so that this will connect right in there. Alright, so for the next one, angle side, it could be that everything's fine. It could be that it connects up just right the way you want it to. And where you've got a nice right triangle. If you do, consider yourself fortunate in that case, but you're not guaranteed a solution. Next case. This could be too long, as you can see here. Alright, so in this case, we could have two possibilities. You could have that this, side swings in, and we've got, pretty skinny triangle there, or it could swing out. We got a little bit of a fatter triangle there, right? It's not clear which case you're going to be in. And this brings us to our final case here. Now we've got, an angle. Side. We've got our angle here. So we have this final case where you have like this one triangle, and note that if it were to swing back, it would miss, and so you do have, in this case, you would have a triangle. So it's an ambiguous case. You could have a side-side angle that does give you a triangle. You could have a set of side-side angles that gives you no triangles, or you could have a set of side-side angles that gives you two completely different triangles. So it's not entirely clear what you have until you start really looking at it. So unfortunately, the side-side angle case is not guarantee you a solution. So we're going to go ahead and round off the lesson with two examples. We've got example 5, the flight of a plane. We've got a pilot flying over a straight highway. All right, so we've got our pilot up here, up in the air, in his plane. All right. And he determines the angle of depression to two mileposts that are 5 miles apart. To be 32 degrees, so angle of depression coming out here. So for the first one, that's the point A, that's 32 degrees, and then the angle of depression to the other milepost, that's 48 degrees. We want to find the distance of the plane from point A and the plane's elevation. So when we say the distance we're looking for is the length of this side right here. How far away is that distance there? All right, so let's go ahead and set this guy up. Okay, so kind of notice that if we were to continue this line like so, using similar, the opposite angle, that's 32 degrees. So because this line's parallel with that elevation, that one will also be 32 degrees. Okay. And then also note that going off of this line right here, this is 48 degrees, which means that this one will also be 48 degrees. All right, so let's find this side using the law of sines. All right, so we've got that this guy is also these two mileposts are 5 miles apart. So in order to really get this to work, we need to know what this angle is right here. We can use that simply by going 180 minus 32 minus 48, which will get us 100 degrees. So now we simply use the law of sines. And so we know that the sine of 100 degrees over 5 miles equals the distance to A. We'll go ahead and call that D, since that's the distance we're looking for. Which goes down here, and that will have sine of 48 degrees here. So solving for D, the distance, we have sine of 48 degrees divided by sine of 100 degrees multiplied by 5. And this gets us 3.77 miles. Alright, so now we want to find the plane's elevation. Note, to do that, we simply form a right triangle with the ground right here. And we can use the 3.77 that we determined from before. And just use a regular trigonometric ratio. So that we'll call it E for elevation. Is what we're after here. So sine of 32 degrees equals opposite over the hypotenuse, the elevation over 3.77. So elevation equals 3.77 times sine of 32 degrees. And that will become, which is an elevation of 1.9978 miles. Given significant digits, we can say that's about 2.0 miles high. Okay. There we go, that's the answer for that one. The next example is a surveying example. We want to find the distance across a small lake. So we'll say the lake is over there, looks like that. And so we've got our surveyor over here measuring with his instrument, not shown. And we want to find the distance across this lake using the information that we have. So you note that he's measured the distance from here to here, this distance from here to here. He's measured the distance from here to here. So he's got those, and then he's got his instrument out, and he's able to read the angle between the two. And I don't know how many of you have any kind of experience with surveying, but they have special instruments that they go out and they can measure to a very good precision. So to find the distance across the lake, we simply are going to use side angle side. Alright, I didn't realize I'd hit the pause button on the record, so let me just go over how far I think we went with this. This is a surveying example. It's another real life example. You would have a guy hanging out right here measuring things. He would have measured this distance, and he would have measured this distance, and then he's got a special instrument that he can use to measure the angle between point B and point A from this perspective right there. And from here we're able to use the law of cosines. This is a side angle side triangle, and fortunately when we set it up, everything's pretty much ready to go. We just got to run through the calculations. We plug all the pertinent information in, and then we calculate through, which I will leave for you as an exercise to do on your own. I apologize for the length of time. I know this is a little bit longer video than we usually do. Thank you for staying with me the whole time, and I hope you got something out of this, and I will talk to you guys next time.